We're almost to the end of week 6 of online classes. Boy, has time flown. Or maybe not. But we're getting closer and closer to the end of the semester. Today we're going to look at tangents again. I know we looked at tangents back in chapter 7 when we did sine, cosine, tangent. The tangent from chapter 7 and this tangent are related, but now we're going to look at how a tangent line relates to a circle. So we're going to apply the properties of tangents to find segment lengths. So here's our circle. Here's the center of our circle. So any segment from the center of the circle to the circle is a radius. So here's our radius. And a tangent touches a circle once. Now this circle has an infinite number of tangents. So why did I pick this one? Because there is a relationship when the point of tangency is one of the endpoints of the radius. So if a tangent and a radius share a common point of tangency, there's a special relationship. And that relationship is a line is tangent to the circle if and only if it is perpendicular to the radius. So we'll come back to if and only if, but let's talk about this again. A line is tangent to a circle if it is perpendicular to the radius. Or a line is perpendicular to a radius if it is tangent to the circle. So if and only if lets you read the sentence in both directions. Either way, here's the important word: perpendicular to the radius. So the tangent and the radius are perpendicular as long as they share a common point of tangency. Now, if I put a radius here, obviously this tangent is not perpendicular to this radius. So this theorem pertains to when the radius and the tangent are intersecting. So a line is tangent to a circle if it is perpendicular to the radius. Vice versa, if a line's perpendicular to a radius, then we know it's a tangent. So how are we going to use this? Well, it means that if you pick any point on the tangent line, doesn't matter where you pick it, and you connect the other end of the radius to your given point or your selected point, you're actually forming a right triangle. So if you're forming a right triangle, then you can use Pythagorean's theorem. Now remember, this sentence goes forwards and it goes backwards. So the Pythagorean's theorem in some cases will be a statement, this is true, and other times it will be a question, is this true? And so we're going to use Pythagorean's theorem, but we're going to use it in two different ways. Now the question usually becomes, okay, so why is this called tangent and how is it related to tangent of an angle is opposite over adjacent? So if you think about the radius and the tangent, because it's all about the radius and the tangent, they're the legs of the right triangle. And if you remember back from chapter 7, the tangent of theta was the opposite over the adjacent, and theta was always one of the acute angles. So these were always the legs. They were never the hypotenuse. So that's how these two are related, because we're concentrating on the legs of a right triangle to deal with this theorem. So again, this sentence goes forwards and backwards. A line is tangent if it's perpendicular to the radius. So we'll only know if it's tangent if we can prove it's perpendicular. We can only prove it's perpendicular if the Pythagorean theorem actually works. So this is a scenario where we're going to check to see if it's a tangent. Determine whether segment AB is tangent to C and vice versa. So we're really asking ourselves, is a squared really the same as a squared plus b squared? Is the Pythagorean theorem really working? So remember, this is kind of a question. Is that a right angle? We're not sure yet, but we're going to pretend it is so we can fill in the numbers. Now you'll notice the radius is 3, and there's nothing here. It's not 2. Only the outside is 2. The radius in a circle is constant, so this is 3. So that makes all of the hypotenuse 5. So C is 5, the hypotenuse is 5. One of our legs is 3, and the other leg is 4. So we're going to check to see if 5 squared equals 3 squared plus 4 squared. Some of you already know this is yes, because this is a Pythagorean triple, 3, 4, 5. And by definition, a Pythagorean triple does, in fact, satisfy the Pythagorean theorem. But we're going to just keep going so you can see it, just in case. So 5 squared is 25, 3 squared is 9, 4 squared is 16. So 25 is, in fact, equal to 25. So we need to finish the question, because we actually haven't answered the question. We've just done the work. Determine whether segment AB is a tangent to circle C. So yes, it is, and then explain why. And that is because we have proven that the segment is perpendicular to the radius. And that's what the theorem says. A line is tangent if we can prove that it's perpendicular to the radius. So we're going to try it again. So again, we're going to check to see if Pythagorean's theorem is actually working. So it's more of a question than a statement. So remember, the radius is 6. The hypotenuse, or what we hope to be the hypotenuse, is 11. Because we don't really know that that's a right angle, we're asking, is that a right angle? So the hypotenuse, or what would be the hypotenuse, is 11. One of the two legs are 6, so we're going to square it, and the other one's 9. We're going to square it. And again, this is a question. We don't know for certain. 11 squared is 121. 6 squared is 36. 9 squared is 81. We get 121 consistently over here. Over here, we've got 36 plus 81. That is 17. 117. That's not equal. That's less than. So 121 is actually, oh, I've got that written wrong altogether. Let's start that all over again. Okay. So 121 is not equal to 117. It's actually greater than, which is what I had, but I said it wrong. So since 121 is greater than 117, not equal to 117, then note, that is not a tangent. I know the picture looks like it, but it's not. Why? Because the segment is not perpendicular to the radius. So our theorem goes forwards and backwards. It's biconditional. It's true in both directions. So a line is tangent, or in this case a segment is tangent, if we can prove that it's perpendicular to the radius. So that's this first one. Can you prove it? Now we're going to go the other way. If a line is in fact perpendicular to a radius, sorry, let me read it the other way, sorry. A line is perpendicular to a radius if it is tangent. I know that looks like I'm not reading it backwards, but I have to have something in here. A line is perpendicular to a radius if it's the tangent to the circle. So now this one is, we know, point S is a point of tangency. They are telling us this is in fact a tangent line, so this in fact is a right angle. It's not a question, it's a statement. We're still going to use Pythagorean's theorem, but this time it's a statement. We know that is working. That is not a question. So again, they've been nice enough to show us that the radii are the same. Okay, now how did we get this 11? How did we get this 5? We did 3 plus 2. We did 6 plus 5. So how are we going to get this hypotenuse? We're going to do r plus 6. So one of my legs is r, so I'm going to square it. The other leg is 9. I'm going to square it. And now my hypotenuse is all of this. R plus 6 squared. Okay, so let's talk about that one right there. So r plus 6 squared is r plus 6 times r plus 6. So now we're going to FOIL it, or distribute. R times r is r squared, plus r times 6 is 6r. So we did this, then we did this. Now we're going to do 6 times r, which is 6r, and then 6 times 6, which is plus 36. We have combined like terms, so r squared plus 12r plus 36. Okay, so let's get back to our Pythagorean theorem. R squared plus 81 equals r squared plus 12r plus 36. R squared plus 12r plus 36. So remember we talked about this in a previous lesson, that if you see an r squared and an r, your first thought should be, I need to factor. And if I need to factor, I need to get all the like terms on the same side of the equal sign. As soon as I try to subtract the r squared from the right, it actually cancels out the left. So it seems that I have to factor, but I don't. So now I'm going to subtract 36 from 81. okay. So 45 equals 12r. And then I'm going to divide by 12. Now you can divide and just simplify. These are both divisible by 3. So you can say 15/4, or I know most of you are a little more comfortable with a decimal, so 3 3/4. So our radius is 3 3/4 units. Okay, so let's try that one more time. Point S is a tangent. So it is not a question, it is a statement. Those two are perpendicular. The tangent and the radius are perpendicular. This will be our hypotenuse, so we need to know how long it is. It's r plus 8. So again, we're going to apply the Pythagorean theorem. We're not going to test it. So one of our legs is r. One of our legs is 12. And our hypotenuse is r plus 8. So we're going to have r squared plus 12 squared equals r plus 8 quantity squared. So we get r squared plus 144 equals r squared, and then remember how we got the 12, we just doubled the 6 they gave us, so if I have an 8 and double it, I get 16r. And then how'd I get the 36? I just did 6 times 6, or 6 squared, so 8 squared is 64. It looks like I'm falling off the paper. Sorry about that. So one more time, r squared, double the 8, 16r, 8 squared, 64. I think again that I'm going to factor, so I need to get all the r squares on one side. As soon as I do, they actually cancel. I don't have to factor. Yay! So I'm going to subtract the 64, giving me 80. So 80 equals 16r. and divide by 16, and the radius is 5. So if they ask you if it's tangent, determine if it's tangent, like a question, then you're questioning the Pythagorean theorem because you'll have all the numbers, you just need to make sure they all work. If they tell you it's a tangent, then you aren't questioning the Pythagorean theorem, you're applying it because you're going to find a missing value. So one more time, let me get that centered up. Maybe? Having a hard time this morning. If your tangent touches your circle at a radius, the radius and the tangent will be perpendicular.